In this video, part 4 of this series, we'll add a reflector to increase the boresight directivity of our system. In part 3, when we simulated the horn on its own, we saw that the boresight directivity was barely any higher than 16 dB. Let's increase this in a new project. Go to Project, insert HFSS Design, some bookkeeping, make sure that the solution type is the driven modal solver and that the modeler units are set to inches. Now let's import the horn and reflector geometries from part 1 and part 2 of this series. Go to Draw, 3D Component Library, Browse, and find your two files, horn Phoebe boundary with radius distance of 0.3, and similarly browse for the reflector IE region with curvilinear meshing, and change its reflector radius to 6 inches. Now you'll see that the waveguide fed horn antenna isn't facing the dish as shown. So first we're going to select the submodel of the waveguide fed horn antenna and go to Edit, Arrange, Rotate. We're going to rotate about the y-axis by minus 90 degrees. Hit OK. I'll invite you to check some of the meshing properties at your own pace. Now go to Modeler, Coordinate System, and we're going to create a relative coordinate system which is offset from the global coordinate system. Hold Z on your keyboard and select a point in the negative Z direction. Now you can see that our global coordinate system is currently being used to reference the horn antenna. We're going to use this relative coordinate system as the basis for our reflector to parameterize the distance between the reflector and the waveguide fed horn antenna. First, let's rename this relative coordinate system as reflector focus. Now let's give the distance that this offset is as a parameter. When prompted to enter the value of this parameter, make it 0 inches. Hit OK. Now we're going to set the target coordinate system of our reflector as being this new relative coordinate system. So here, in target coordinate system, change it from global to reflector focus. Again, I'd like to invite you to check some of the meshing properties at your own pace. Let's add a solution setup. So go to HFSS, Analysis Setup, Add Solution Setup. In the General tab, let's set the meshing frequency to 10 GHz, which is our design frequency, and set the maximum number of passes to 1. To save time with this simulation, we're just going to use one pass in this case. Click OK. I'm going to save this project and then go to HFSS, Analyze All. Feel free to pause this video while your simulation completes. Now that my simulation is finished, I'm ready to perform some post-processing. The two key focuses will be overlays of current and electric fields, and then a 3D radiation pattern which will have a greater directivity. Also, we hope. First, let's get an overlay of the current on the reflector. Enter Object Selection mode by pressing O on your keyboard or going to Edit, Select Objects. Then go to Edit, Select by Name, and select Reflector 1. Once this is selected, it is easy to get an overlay. Just go to HFSS, Fields, Plot Fields, J, and MagJ Surf. Surface Current, click Done, and you should see a plot pop up as shown. You can see the magnitude in amperes per meter, and we can animate this plot later on to see how this varies for different phases. Let's do a similar step by selecting the YZ plane, and then going to HFSS, Fields, Plot Fields, but this time picking E and Maggie for magnitude of electric field. Click Done, and we should see the magnitude of electric field pop up as shown. To modify the attributes of a field plot is really easy. Just go to HFSS, Fields, Modify Plot Attributes. Pick your plot. For example, for JSurf, I might pick this plot, and I might change the scale to a logarithmic scale. I can control other aspects as well through the other tabs. Once you've modified your plot attributes, go to HFSS, Fields, Animate. Now we want to set up an animation which is not based on normalized distance, as I've used before, but have it based on phase. For these phases, click OK. You should see for different phases that the magnitude changes. Feel free to speed up or slow down or step through this animation at your own pace. Now let's get a 3D radiation pattern as shown on the next slide. Go to HFSS, Radiation, Insert Far Field Setup, Infinite Sphere. Let's rename this as 3D and change the phi sweep to go from 0 to 360 degrees. Click OK. Now we're ready to obtain this plot by going to HFSS Results, Create Far Fields Report, 3D Polar Plot. Now we want the geometry to be 3D as we just defined, and we want to see the directivity in dB. Click New Report. And here we go, the moment of suspense. We notice that the directivity is a lot closer to 28 dB in this case. If I just change the number format of our color key, change it to decimals, and allow for more decimal places, you'll notice that the maximum is closer to 27.578 dB, which is a lot higher than we had previously. As shown in previous videos, you could overlay this onto your original design to increase your understanding of the system. Thank you for watching.